This might look like alien technology or a magic trick, but it's not. It's one of the finest examples of material science and engineering. They're called shape memory alloys, smart materials that can be programmed to remember any shape. The most common shape memory alloy is called nitai, or nitinol, which is composed of nickel and titanium atoms. It was discovered in 1959 at the Naval Ordnance Lab by William J. Bueller. When the atoms of nickel and titanium are mixed at high temperature and then cooled, the atoms will form arrangements that we call crystal structures. The different crystal structures of the material control the mechanical properties of the material, like its strength and flexibility. Shape memory alloys can remember their shape at specific temperature because the material undergoes a phase transformation. Phase transformations are changes in the state of a substance from solid to liquid to gas. An example of a familiar phase transformation is boiling water changing from liquid water to gas and melting ice transformation from solid to liquid. These phase transformations are considered irreversible. Similarly, shape memory alloys can transform their shape when triggered by heat or stress. This allows the shape memory alloy to return to its original form due to a reversible solid-to-solid phase transformation between the martensite phase and the austenite phase. Before we can understand the mechanical properties of shape memory alloys, we first need to understand how conventional materials behave under stress and strain. Polymer materials like rubber bands are considered elastic materials. This means that the materials will return to their original shape without any damage. Metal materials undergo plastic or permanent deformation upon stretching and bending, which results in permanent damage to the material. Shape memory alloys have two special features, the shape memory effect and the superelastic effect. The superelastic effect is a magnificent property of shape memory alloys that allows the material to remember its shape when you remove the force from the material. The property occurs when you are testing a shape memory alloy that is already in the high temperature austenite phase. If we look at the stress-strain curve, we can see the superelastic materials are strong like metals but can reach large strains like polymers. Superelastic materials are used by biomedical engineers to develop medical devices that will be implanted into the body because the SMA device can be squished into small microcatheter tubes and then the SMA device remembers its shape when inserted into the body. For example, here is an SMA stent formed from a 2D thin film material. SMAs are also electrically conductive and can be integrated into circuits to build stretchable electronic devices. If you stay within a superelastic strain limit of 8% for nickel-titanium SMAs, the material can go through the transformation reversibly for millions of cycles. Now comes the magical part, the shape memory effect. When we stretch the material, we are transforming from twinned martensite to detwinned martensite. When we apply heat to the material, we are inducing the transformation of the material from detwinned martensite to austenite. When we cool down the material, we are transforming from austenite back to twinned martensite. This reversible transformation allows SMAs to produce large forces, which makes them useful to move things at the nanoscale. STEM teachers should teach about shape memory alloys. They are incredible materials that bring motion and shape-changing abilities to life. SMAs act like magical materials, responding to heat or stress, providing students the opportunity to control movement in various applications. Integration of SMAs into the classroom encourages creativity and design thinking among K-12 students. Khanjur's engineering magic kits are intended to introduce K-12 students to the fundamental material science concepts through hands-on SMA labs. Our labs will provide students the exciting opportunity to innovate and invent new solutions to real-world problems. Khanjur's engineering magic kits are fun for people of all ages. Embark on a magical journey through the wonders of shape memory alloys in your STEM classroom. Join our enchanting marketing research study by scanning the QR code and tell us how you would use an SMA in your classroom.